Hi everyone, I'm back here for the part 2 of standing waves, and I've gone through waves with string tight at both ends. Second one, pipe open at both ends. I'm still looking forward to your answer as to why the wave is being reflected at the open end. Now the third case that I want to go through today is this case where you have a pipe open at one end and closed at the other end. So the particle cannot move into the pipe. So that's why it is forced to be a node over here. And this point over here, like the pipe open at both ends, it will be allowed to move with maximum amplitude. And that's why it's an anti-node over there. And if you were to force an anti-node and a node over here, the waveform with the longest wave will look like this. And then the next one will be here, and this next one will be here. At this point of time, I'd like you to take a look at the pattern. From here to here, how much of a wave do I add in? So if you take a careful look, do you agree that it is actually half a wave? Now let's check this idea. This wave ends over here. From here to here, can you see that it's another half a wave? Now that is exactly the same kind of pattern that you see over here. Remember this case, to this case, to this case. You add half a wave to this, you get this. You add another half a wave to this, you get this. So this is a very useful rule, if you want to say if it is a rule, that you can remember to go from one wave to another wave to another wave. You always add half a wave. For some reasons in standing wave, this is the magic number, half a wave from one to the next harmonics. These are what we call harmonics. Alright? Now, I always feel that in order to get the expression for the wavelength, it is easier for you to identify how much of a wavelength. Like this one is a quarter of a wave, and it is equals to L, then you work on the wavelength. It is always very difficult from my experience for you to work out this wavelength equals to 4L upon 3 just by looking at this. It is always easier for you to say 3/4 of a wave is equals to L, and therefore wavelength equals to this. It is always easier. Proven to be a much more error-free method than trying to spot what's the wavelength immediately without going through this step over here. Then the frequency, something interesting, if you take speed divided by the wavelength, you'll find that the frequency is equals to V upon 4L, 3V upon 4L, 5V upon 4L. You might have noticed this very interesting trend. I realize that the reflection is not helping, but this is 1V upon 4L, this is 3V upon 4L, this is 5V upon 4L. So this is 1 times, 3 times, not 2 times, 3 times, not 2 times. This is 5 times, not 4 times. So what am I trying to say over here? That is the even multiples are missing. The even multiples are missing. As compared to the previous case where you have wave, string tight at both ends, string pipe open at both ends, you have 1 times the first wave, first frequency, 2 times, 3 times, 4 times, 5 times. All the multiples exist. But for this one, only odd multiple exists. And we're going to do a question later on to check this understanding. Alright? Now, I'm going to move on to miscellaneous examples. It's a little bit, it might be a little bit dark, so you might have to turn up your brightness on the screen. So, what is different over here is this. For these examples, I changed the frequencies for the same length of pipe. Over here, I have the same frequency. I don't change the frequency, but I increase the pipe length. Now this is a typical example that IB loves to use where they lower the water level and then you hear loud sounds at this position. Why loud sounds at this position? Because these are the positions where the frequency and the wavelength of the wave that is being sent in matches the resonant frequencies of the pipe. Resonant frequencies meaning the frequencies that obeys the open end, closed end, anti-node, node condition. So when it matches, it will be a loud sound. Now let's take a look. This is exactly the same as that, and that's why I'm doing this after that. Just tilt it 90 degrees, you'll see that this is 1/4 of a wave, 3/4 of a wave, 5/4 of a wave. And what do you notice from here to here? How much of a wave do you add? It's wavelength upon 2. From here to here, can you see that it's another half a wave? So the magic number over here, half a wave, comes in as well in this situation. That whenever you have the pipe increases in length by half a wavelength, you will have a loud sound. So a typical question will be, you don't even need to know which harmonic it is. So I can give you situations where the wave, the question says that there's a loud sound at this position, this is not given. And then the next loud sound happens when the water is lowered by 30 centimeters. Then you're asked to find the frequency. So what you need to know over here is that you need to identify that this is equals to wavelength of 1,2 and therefore it is 0.6 meters. You don't need to know whether this is the 3 lambda upon 4 equals to L case or 5 lambda upon L4 equals to L case. You don't need to know, because you know that from here to here it is always half a wavelength, and that's all you need to know. Okay, so this is a very important thing you need to recognize. It's very popular in IB. The half a wavelength change in length of pipe will go from one loud sound to another loud sound. Alright, for that one, it's a different case because that case is the same pipe length, but I changed the frequency. This is the same frequency by changing the pipe's length. So just be careful about the difference between these two in case you start to get confused. Alright, so this is more or less the important stuff about standing wave. One more examples which I promise you that I would like to highlight this question to show the difference between the two pipes. Pipe open at both ends and pipe open at one end. So let's take a look. So I got two pipes, pipe A, pipe B. Let's think. 1000 Hertz, 1200 Hertz and 1400 Hertz are three adjacent. That means it's, say for example, the 10th harmonic, 11th harmonic, 12th harmonic. So it's like the adjacent loud sound produced when you change the frequency. For pipe B, it will be 1002 Hertz, 2000 Hertz and 2800 Hertz. So these pipes over here, these two pipes over here, one of them is a pipe open at both ends, one of them is pipe open at one end. Which one is which? Probably you'd like to pause the video at this point of time and check, see whether you can get the answer and before we move on. So after finding which pipe is the open pipe and closed pipe, I'd like you to find the frequency of the first wave, the fundamental frequency. That's when for pipe open at both ends, you'll be V upon 2L. For pipe open at one end, you'll be V upon 4L. So what's that frequency? Pause now and check, see whether you can find the answer. Right, I hope you can find the answer. Let's do a quick check. Can you see that this is 5 times 200, this is 6 times 200, this is 7 times 200. Adjacent multiples of the same fundamental frequency. Whereas this one is 3 times 400, 4 times, or rather 5 times 400, and this is 7 times 400. So this is how you find which one is the open pipe, which one is the pipe closed at both ends. So this one, odd multiples of the frequency over here. So 400 is the lowest of frequency, which is fundamental frequency, and 357 means that this is the pipe open at one end. Odd multiples. This is adjacent multiples, so it is the pipe open at both ends. Alright? So this is how you can determine whether the nature of the pipe. Okay? A very interesting example that tests whether you understand the difference between those two pipes. Cool, so I hope that with the two-part videos you will be having a better understanding of standing waves. I will upload more questions so that it helps you concretize what you know and also to surface what you may not know. Alright? Enjoy learning.